So for the direct research for capstone project, Nathaniel Bernal and myself, Gregory Jones, implemented some trajectory optimization methods, specifically direct collocation methods, including trapezoidal and Hermite Simpson collocation on the SO101 um, robot arm. And um, I guess like at a high level, trajectory optimization, more intuitively is the goal is to minimize or maximize, um, essentially optimize some kind of cost function or particular quantity related to motion. And some examples of this include quantities like minimizing time, energy, or joint torques over the motion from one robot state to another. And in addition, there are typically constraints that need to be satisfied too, such as joint position limits, obstacles that shouldn't be obstructed, avoiding exceeding actuator torque limits to not damage the motors, and then also satisfying feasible motion um, related to the physics or the dynamics of the physical robot. So those come in the form of constraints too. And the goals of the project were to familiarize ourselves with a few trajectory optimization methods and their trade-offs, um, and then implement two direct collocation methods, particularly trapezoidal and Hermite-Simpson, test this in simulation and hardware, and compare the results. So this is the SO101 robot arm that we used. On the left is the physical robot arm. On the right is the simulated version in Majoko. And it has 6 axes of control, each using position-controlled servos. At a high level, system architecture includes trajectory optimization, sampling, and then the simulator or physical hardware. So on the left-hand side here, you have the inputs, which will make a bit more sense as I go into more detail on the algorithms, but it includes the dynamics, start and end states, number of trajectory segments, the bounds, which would be like position, limits, and the cost function. And then the output of that, of the trajectory optimization, are continuous state and control trajectories. In this case, the control is actually the joint torques. Then that gets sampled at a particular period, 20 milliseconds, for our experiments. And those generate discrete sampled trajectories, and those well, specifically the position sample trajectory gets sent to the position controlled servos because they can't take any other target input. Ideally, they would take torque, but they position controlled. And then in the simulator on hardware, these servos would then output appropriate torques to the physical links or the joints of the links, and then get feedback um, in the form of joint positions internally in the servers that had internal PID loops running. Now, there are a few trajectory optimization methods that we had a look at. There's dynamic programming, indirect methods, and direct methods at the highest level. I'll come back to dynamic programming, but the difference between direct methods and indirect are generally there's a phrase that goes that direct methods discretize, then optimize, and indirect methods optimize and then discretize. So for indirect methods, you have what are called optimal control necessary conditions that are solved by some root finding method. And these are generally more accurate than the direct methods. However, you have to explicitly derive these necessary conditions for every kind of, well, for every particular problem. So changing the problem means a rederivation. However, the direct methods don't have this issue. They're a bit more adaptable to the problem. And so you, in this case, discretize the state and control trajectories and then solve the problem with using a nonlinear programming solver. And the process of getting the problem into a discrete form is called transcription or collocation. However, as I mentioned, they're generally less accurate um, than indirect methods. And for dynamic programming, that ends up actually creating or finding a um, optimal policy that takes any state in the state space as input and then outputs the optimal control. And that's known as like the global solution. And if you then want a particular trajectory, you need to follow that policy uh, from some particular start state until it reaches the end state to generate a single trajectory. Whereas these other methods that generate a single trajectory, that's the open loop solution. And open loop solution methods that they don't guarantee a globally optimal solution. They're just locally optimal. Whereas dynamic programming has global guarantees. And then under direct methods, you have shooting methods and collocation methods. For shooting methods, the main idea behind that is in order to satisfy the dynamics of motion of the physical robot, uh, numerical integration or simulation is used. And then single shooting uses a single trajectory segment, whereas multiple shooting it splits it up into multiple trajectory segments, which actually improves the accuracy of the simulation. However, both methods are still um, sensitive to their convergence to solution is sensitive to the initial conditions. Um, However, the multiple shooting is less sensitive. And then for global collocation methods, fit a single higher order polynomial to the entire trajectory. And they're generally quite accurate, but more difficult to implement than the local collocation methods. So if for the local methods, let's see here, you have basically the idea there is to, instead of a single polynomial, you split the trajectory into multiple segments, and then each segment you fit a lower order polynomial. Um, and which makes it quite a lot more simple to implement. And the difference between trapezoidal and Hermite Simpson is just that Hermite Simpson uses a one order higher polynomials. And yeah, I'll go into more detail into the Hermite Simpson and trapezoidal. So the solution or the output of this optimization process is the state and control trajectory. And the first step in solving it is to discretize. In our case, we uniformly discretized into segments, trajectory segments. And then the the main idea is, as mentioned, like fitting polynomials, but more formally, a spline is fit to each particular trajectory, and a spline is a piecewise polynomial function. So you can think of it as concatenated polynomials, one for each trajectory segment, and the problem gets solved using a nonlinear programming solver. A cost function needs to get minimized, which depend on the discrete state and control variables, which act as the optimization variables. They need to be selected. And then several constraints need to be satisfied too. So the constraints include dynamics of motion, the boundary conditions apply to the start and end states, and then path constraints, so just bounds on the state and control over the entire motion. Um, and then the lower left equation here is just basically the spline in polynomial form being approximated. And then on the right here, this equation is the dynamics function. And these direct methods generally benefit from a good initial guess, which I'll discuss a bit more. One other thing worth to mention is selecting the number of time segments. So increasing it increases the accuracy, but also increases computation time. So reducing it has the opposite effect. So there's a trade-off. Now, both these methods need to formulate a nonlinear programming problem. So in the general case, that involves a cost function j here um, that takes the c value, which is just represents the optimization variables that need to be selected, and then these constraints need to be satisfied. So this g function, it's a function of the optimization variables, could represent the dynamics that need to be satisfied, and then the actual optimization variable bounds would be like the bounds on the joint states and torque limits. So for trapezoidal collocation, the state trajectory is approximated using a quadratic spline, which you can see on the bottom right here. Generally looks quite smooth. And you have these knot points, which are the values in between the polynomials, like they're basically the endpoints of each segment, trajectory segment. And then the control and state dynamics functions are approximated using a linear polynomial spline, which you can see on the top right here. And if you integrate the dynamics function, and you end up getting the state function. And then these equations here basically represent what I just said. So f is the dynamics function, linear polynomial approximation for that, linear polynomial approximation for the control, and then integrating the dynamics function gives you a quadratic function for the state, and using the state function you can get this this constraint here, which is known as the defects constraint, where you only consider the endpoints of each trajectory segment, and this ensures that the dynamics are satisfied. Now, formulating the actual nonlinear programming problem, you have as the optimization variables, the discrete state and control variables. You then discretize the cost function. In this case, we selected the cost function as this the square of the which ended up being the square of the norm of the control input, which is taken to be the torque, the joint torque vector, and integrated over the trajectory, and then that's approximated using trapezoidal quadrature. And then in terms of the constraints, you have this defect constraint to satisfy the dynamics. Start and end states are equality constraints. Then finally, there are bounds on the state and control throughout the motion. So here's the control and up and lower bounds on each of the state values at each collocation point. Then for Hermite Simpson, it's a similar process, just using one order higher polynomials. So in this case, the control and state use a quadratic spline. There's quadratic functions. I integrate the dynamics function to get a cubic function, and then similarly get a defect constraint to satisfy the dynamics. However, you also need this midpoint constraint to approximate the midpoint in order to calculate the midpoint dynamics value. And then similarly, compared to trapezoidal, you then have these midpoint state values as well as the midpoint control values, midpoint of each trajectory segment. And then for the cost function, it's approximated with Simpson quadrature. Start and end state constraints are the same. However, the bounds on the state and control also include the midpoints, and then there's the defect constraint, and then there's also the midpoint constraint. Yeah. So just putting this all together into the trajectory optimization system, taking all the constraints, so the start and end states, the boundary constraints, then the path constraints, and the defect constraint from the dynamics model. Those all create the constraints for the nonlinear program. And then you have the cost function that needs to get minimized, and then guessing the solution is done using linear interpolation between the start and end states. And so that's done over all the optimization variables, which depends on the number of segments. And then the output is the solved optimization variables, which consist of the discrete state and control variables at the collocation points, and those are then used to generate a spline or splines, which represent the continuous trajectories. And then these continuous trajectories need to be sampled. So I mentioned previously they're sampled at a fixed time of 20 milliseconds, and this duration was independent of the duration used for the trajectory segments. So you could change the number of trajectory segments and the sample time wouldn't change. And then to actually sample these splines, the polynomial interpolation needs to be used using the functions, those function approximations that I mentioned previously, based on linear, quadratic, and cubic polynomials, which were implemented and in software. And then um, let's see. So to actually sample a spline at a particular value, yeah, I wrote code to look up the particular time segment and the associated polynomial coefficient data to actually then interpolate the value. And then one class worth mentioning for was the quadratic spline, which was ended up being used for both algorithms, and it was designed to support either setting the coefficient values based on two knot points and a gradient value in the case of trapezoidal, or two knot points and a midpoint value. So the knot points again are just the values of the function at the endpoints of a trajectory segment. For the optimization software, the low-level library was RPopt for the solver, and then IFopt was the wrapper around that, which created a convenient interface to RPopt for defining our NLP problem. Part of that required actually deriving Jacobians of the constraints for each algorithm with respect to each of the optimization variables. So quite a large Jacobian function, but it was sparse. So a lot of the values were zero, and the details of the math behind that are on the report, but ended up using eigen sparse matrix to support that. And then the Hessian, or you can think of it as a second order Jacobian, was also required by IPOP, but this was configured to be numerically approximated. And then there were three classes that were extended to make defining the problem useful. So they included the constraint set that was used for the defect constraint, and then the variable set was extended to create a trajectory variables class, and that was used for a number of state and control classes, which also differentiated based on whether they were for midpoint values or not point values, which made it easy to separate them. And then there was also a cost term class that was extended based on calculating the cost term and also Jacobians each algorithm. And then Pinocchio was used for estimating or calculating the dynamics as well as Jacobian values relative to like control and state inputs. For the simulation system, I created a simulator class that included two main parts of the simulation event loop and then a Majoka simulator. The Majoka simulator took as input a XML file representing the model of the robot, which included the servos, the position controlled servos, as well as the physical model of the arm. And so when this Majoko simulator was stepped as part of the simulation loop on the left, that would do some calculations like involving the PID loops of the servos. So I didn't have to write anything for this. This was kind of internal to the Majoko simulator. The only thing that needed to be done mainly there was loading the model and then stepping the simulator. And then in the simulation event loop, quite a bit of the work was done here, which involved updating these timers, or three timers classes that I ended up creating based on the timer class. And the idea here is to basically call some functionality at a particular period or rate based on simulation time or the simulation clock. So when basically these timers would be updated or checked to be updated, and then the simulation time was stepped. And so the timers included a timer for updating the position target that was taken from the sample trajectory and then sent to, you can see sent to the servos. And then there's also a timer to update the display based on a configured um, frame rate, and that used an OpenGL-based library. And then also a timer for um, caching or updating data recorded based on the trajectory, the actual trajectory, or the actual motion of the robot arm. And that ended up being saved to a separate file on exit of the software. This was on C++. And in terms of the hardware system, so Nathan actually did more of this, but I was still quite involved, so I'll still speak about it somewhat. So the main inputs were the sampled trajectory, and that was then followed um, over time using the software, and then the main output was a command packet over serial communication to the controller board, which then communicated with the servos. And so in this hardware event loop, it would pull the uh, current target or most recent upcoming target from the sample trajectory, and then it would convert it to servo tick values from radians, and that was based on calibration mapping that I wrote. And the calibration file was generated using a Larobot script that already existed that we used. But I wrote the code to pass the calibration file and then actually do the mapping from radians to ticks. And those codes actually send the packets or positions, fill the messages with the target positions and then send it to the control board. And that ended up using low-level like Linux system calls, using sockets and writing and reading commands. And then on the reading side, uh, reading the socket of the serial communication to get data for the actual followed trajectory that included position and velocity. And so that ended up being saved to a separate file too. So that logic was something I wrote also. Now moving on to the actual problem or experiment. So top table includes input data. Duration of the trajectory was about 2 seconds. Input state was the home position um, with no motion. Final state was just offsetting the first joint by 45 degrees. Lower and upper bounds were just based on position, mainly positive and negative 45 degrees, except the final joint actually had a lower bound of 0, which was the closed gripper position, and then a maximum open position of 2.25 radians. And there were also limits on the control, which was approximately 1/3 of the maximum torque of the servos, which you can think of as the rated torque. And then the lower table is some data about the NLP problem and the actual iteration process. So these values were recorded for trapezoidal algorithm with 10 segments, 10 trajectory segments, as well as 20. Hermite Simpson was just 10. The one thing you'll notice is that doubling the trajectory segments for trapezoidal actually creates a similar number of optimization variables and collocation constraints between trapezoidal and Hermite Simpson. Um, However, in terms of differences of like solve duration for trapezoidal, 10 trajectory segments, it's only 3.2, 3.3 seconds. Doubling that, it almost basically triples the solve time. However, Hermite Simpson with 10 trajectory segments, it still takes longer, but theoretically the error is lower and the motion's actually smoother because the first order derivative of the um, trajectories are well, like the dynamics trajectory is continuous, whereas for trapezoidal it's discontinuous. So you actually get smoother motion with Hermite Simpson. And from this improved accuracy of Hermite Simpson helps to uh, optimize and approximate more accurately a lower cost value, the lowest cost value out of this data. Okay, and then looking at the solution trajectory, so this is the state trajectory for the trapezoidal collocation. Um, on the left-hand side, position, and then the right-hand side, velocity. So left-hand side is where all the constraints are. All the bounds are satisfied uh, correctly, and the start state was 0, end state 0, except um, the final joint being about pi over 4, 0.78 radians. And yeah, so that looks good. And then one thing you'll notice with the control, so the control bounds were satisfied here with the control trajectory. You see the mid section of the trajectory, the control is quite low. So keep that in mind when I show the demos. And then tracking errors is for position trajectories. So in general, the on hardware, the errors were larger, probably by approximately 2.5, a factor of 2.5. Error in simulation was about 0.06 radians or 3.4 degrees. On hardware, zero point 0.1, about 0.17 radians or 10 degrees. And let's see if there was something else I wanted to mention here. Oh, and just a reminder, the position trajectories were used as the targets, so that was actually what was being followed by the simulation or hardware. Um, Velocity tracking errors, these are a bit more similar compared to simulation and hardware. No constraints to comment on here. And then demo-wise, you can see the robot actually like intuitively, it's lifting up during the middle section of the motion to, which is where, the servos wouldn't need to apply as much torque. So that checks out. Oops, come on. Oops. Uh, Okay, and then for Hermite Simpson, um, these are the state trajectories, and um, the solution state trajectory. And so the bounds in this case are also satisfied, which is good. And end state makes sense with about 45-degree offset. Duration is 2 seconds and 0 start state. Then something's not. Okay, then looking at the control, one thing with, so everything is it's kind of similar here. One thing worth mentioning is you notice for the solution for Hermite Simpson, the number of collocation points is about double, which makes sense because they're midpoint values. And then you also notice this control doesn't actually satisfy the constraints in this section over here. And that's because the bounds are only applied at the collocation point. So that's just a limitation of the actual discretization and algorithm. So it needs to be, if it's not sufficient, you can increase the number of trajectory segments. And then, let's see. So, yeah, for Hermite Simpson again, got there's a minor error in the title here, but it's the trajectory tracking errors for Hermite Simpson. There's simulation and hardware, and um, the errors are actually kind of similar to trapezoidal, slightly larger though. So zero point 0.08 here is about 4.6 degrees, and on hardware, 0.25 is about down here I should say is about 14.3 degrees. And then um, these are again minor error here, but this is focusing just on the velocity errors. And again, these are kind of similar between simulation and hardware. So demo-wise, the motion looks quite similar. So it lifts up like that. Also on the simulation, so similar motion there. And the main sources of error and categories are inaccuracies between the simulated physical dynamics and then the controller or control system. So for the first point, we didn't really do any, well, I should say we didn't do any system identification, for like calculating link inertias or masses or dimensions. So we just used what was in the existing um, model file, which could easily have some inaccuracies. The models didn't include any friction or backlash or communication latencies. And then there are also errors associated with approximating the state dynamics using splines or a spline. And then the control system, servos, servers were position controlled. They weren't torque controlled, so they had to take position input, whereas, the actual optimization problem assumed torque controlled. Um, so, if it's not the actual robot isn't torque controlled, then it's not taking the solved control trajectory, then there's going to be some discrepancies, some errors related to that. And then using independent position controlled servos instead of something like model-based controller like computer torque, um, means low performance. So computer torque would definitely improve things, improve the tracking. So, so the main goals were achieved in this project, namely going over the trajectory optimization methods in general, implementing two of them, Hermite, Simpson, and Trapezoidal, simulating and simulating the trajectories and also testing it on hardware and then comparing the results. And then future work would be to extend the comparison analysis between the two algorithms, so more thorough analysis on the number of segments that can be used and what's a good value for that. And then theoretical error approximations of like the spline. Um, how good are those spline fits to the dynamics, and then also reducing the tracking errors, as mentioned, using something like computer talk. And then more complex problems could be applied, so model predictive control or enabling a legged robot to walk. And that's it. Thank you very much for listening.